I'm always a little bit nervous giving a talk on free will as a physicist. I'm not nervous about speaking about what the title of the talk has to say. Does science leave room for free will? What I'm afraid of, though, is that when people hear that a physicist is going to talk about free will, they're not expecting that talk. They're expecting a talk on, say, the physics of free will. Exactly how is it that the immaterial mind yanks around electrons when people think and decide and choose? What exactly would we need to adjust in the equations of the Lagrangian of the Standard Model to make sense of how electrons interact with immaterial forces? That is not the talk that I'm going to give today. But I hope that throughout the course of the talk, I'll present an argument for why that's not the talk I'm giving, and why, in a certain sense, that there's a lot more work to do before we could even hope to give that talk. The talk I am going to give has three parts. First, I'm going to spend some time talking about physics and looking at some arguments that are often heard in both in sort of popular presentations and more detailed presentations from contemporary physics against the very possibility of free will, usually along the lines of arguing for some form of determinism or some aspect of the idea that the physical laws don't allow for space for anything like free will. Then I'm going to step a little bit out of my comfort zone and talk about neuroscience, not being a neuroscientist myself. But I'm going to draw on a lot of good work and research by philosophers and neuroscientists themselves, and talk a little bit about one of the most common, again, popular ideas people hear about the relationship between science and free will, neuroscientific experiments that claim, in some cases, to test for the possibility of free will and find it lacking. And finally, I'm going to shift and in a certain sense, change the argument around. Not about how is it that we can use science to find or not find free will, but is it even possible to do science if we don't have something like free will? And what does it very mean for us as human persons to be able to engage in this very endeavor that is the contemporary sciences? Finally, I'll try to conclude very briefly and maybe offer some hints or thoughts in the direction of that physics of free will, but no guarantees. So, shifting from the first portion, talking about the physics and arguments from physics against the possibility of free will. One common version of this that perhaps you might even see on something like a YouTube video, a popular presentation of physics, is roughly the block universe vision that people claim is the clear and obvious reading of special relativity. Roughly speaking, special relativity says that there is no preferred three-dimensional space of simultaneity. There is no universal now that extends through all of the universe. That each observer, in a certain sense, has their own now. What is simultaneous to someone depends upon how they are moving. And for an individual observer, that space of simultaneity might change depending on how fast they're moving. So the claim is that this can only be made consistent if the universe is not a fixed three-dimensional structure moving through time, but a fixed four-dimensional structure, in which time is really just another version of space in some mode. That it's just, depending how we look at it, the difference between space and time. Since space is real in all directions, I was just in Lublin this morning, which is quite far away, and I'm fairly confident that it's still there right now, that there is real space in every direction, and I can talk about things that exist very, very far from here. There's a reality in every direction when we think about space. The claim is that the same thing is true of time. While we familiarly think that there's something different about the past and the present and the future, the past being those things I know have happened and I can't change, the present being the things I'm working with now, and the future being things that are open and undetermined yet, that's an illusion. Because time is just some reimagined version of space, it's already there and already fixed. Just like the distance from here to Lublin and the details of the beautiful town in Lublin are already fixed. There's a certain sense in which the future is just as fixed. So this is in one sense, easy to understand, but again, also sort of hard to get your head around. But the implications are that the claim is that the future is already real, already fixed. Every decision I am going to make in the next, say, 5 minutes could have and probably has already been observed by somebody else, and in their simultaneity has already happened, perhaps. Now, there's messy details to work out there, but the idea is that since the future could potentially have already been observed by someone else, then the future is already there. And this is a sort of contemporary version of various forms of arguments for that physics at its root needs to be deterministic in some way. But you might say, what about quantum mechanics? Doesn't quantum mechanics imply that the world is random and indeterministic? Well, many, when presented with this quandary, would argue and say that, well, in a certain sense, relativity sort of trumps quantum mechanics here. There's something about the indeterminism of quantum mechanics that has to give way in the light of relativity. Now, for instance, many people are aware of the fact that we have not quite figured out how to reconcile quantum mechanics and gravity. The idea of this fully finished unified theory of physics. But most people presume that special relativity and quantum mechanics work perfectly well together. We have relativistic quantum mechanics, which is the foundation for what is modern quantum field theory, which is what we use in experiments like the Large Hadron Collider, where we're testing the foundations of modern physics. The thought is that we have reconciled these two aspects of reality or physical theories completely, and that since relativity implies this necessary block universe picture, that we can make sense of that in the context of relativistic quantum mechanics. But in a certain sense, the difficulty of the reconciliation between quantum mechanics and relativity is not at so much these high energy superspeed cases, but actually at much slower, more mundane, in a certain sense, experience. After the initial if you look at the history of quantum mechanics, after the initial sort of shock and confusion in the early 20th century about the deeper significance about quantum mechanics, there was this sort of collective existential crisis among physicists. The focus for most of them turned away from thinking about the meaning and foundation of quantum mechanics to just putting it into practice, working it out, figuring out its implications for nuclear physics and condensed matter physics, high energy physics, and other problems. But a small but very creative community of physicists kept asking some fundamental questions about quantum mechanics itself. The work of John Bell in the 1960s, they proposed this idea that you could test for the possibility of certain kinds of extremely weird features about quantum mechanics and provide an actual experimental test about whether these weird features actually manifest in reality or not. And this is not simply the weirdness of uncertainty and the fact that the results of quantum mechanical experiments are probabilistic, but these are questions about the idea of non-locality in the activity of quantum mechanics. There is a notion that's called entanglement, where you can take a state of, you can interact quantum mechanical states, in practice usually some collection of electrons and photons, in such a way that they don't act as one thing or a couple of things, they don't act as several individual electrons, but they have a sort of unified collective activity, such that the action on one has immediate implications on the other. So Bell proposed that there was a way to test this experimentally, and through the work of some amazing experimental physicists in the 70s and 80s, they were able to confirm that this inequality that Bell measured about that was able to say that if the world were ultimately classical, ultimately local, such that there is the impossibility of this sort of immediate action at a distance, this inequality should be satisfied. But in fact, when you measure it, it is violated, as quantum mechanics predicts. And not only that, they extended this in an amazing experimental tour de force to rule out all sorts of possible loopholes, which involved taking these entangled states, a couple of photons or electrons, and separating them by huge distances. In this case, it's usually photons going through, being separated very, very far away, and measured in such a way that they are so far apart and measured in close enough time that there is not time for any light-like signal, any signal that would obey the laws of special relativity to communicate between them. And yet still you find this sort of correlation between these measurements that is impossible in classical physics. That there is seemingly this faster than light communication, immediate communication, or at least faster than light communication between the parts of these entangled states. This spooky action at a distance is actually the thing that Einstein was so frustrated about with quantum mechanics. And yet it is something that we have been able to test and seems, as best we can say to be true on these very particular cases. But more fundamentally, this type of experiment brings to the fore important questions about time, it places time and indeterminism back in the forefront, as there is this strong asymmetry in the way the measurements take place. And an implicit necessity for a certain kind of freedom for the experimenters. The people who design these experiments describe this. There needs to be a certain independence of the person measuring these devices. So it seems, at least there's strong arguments, you say, that there is still great tension between quantum mechanics and special relativity that has not been fully resolved. And yet, deeply down, I would say there are still a lot of physicists and philosophers of physics as well who really, really wish the world were still deterministic. It would just be so much cleaner. For those unsatisfied with this spooky, superluminal action at a distance and seeing these violations of relativity, there are still some philosophical options, but they each come with other just weird and spooky features. One that is commonly known is or known in some circles, is the many worlds interpretation of quantum mechanics, in which each experiment that on the surface of it has various possible outcomes, and there's a probability of each outcome happening every time you run the experiment. In fact, what happens is that when the experiment is run, every outcome happens. It's just that, in a certain sense, the universe splits into pieces, depending on for the different outcomes of the experiment. More properly speaking, it's that we only actually exist in one small slice of the nearly, if not actually infinitely dimensional space that is the wave function of the universe. And so our experience of 3 dimensions of space and a dimension of time are simply a weird shadow of this much nearly infinitely dimensional space. And so our very existence, and with it, the very appearance of our ability to choose, is actually just an accidental feature of this fixed and actually determined infinitely dimensional space. So, in a certain sense, it means that every choice we make is no choice at all. All of our options are actually taken, but in mutually exclusive branches of this absurdly massive, infinitely dimensional wave function. I mean, another sort of option that might get around some of the conclusions of these experiments based off of the work of John Bell would be for a sort of super determinism, as he describes it, where there really is only one universe, not this branching many worlds interpretation, but that in some way every outcome, there's only one universe and only one outcome for every experiment, but everything that happens in every single test, including every free choice of the experimenters or some random stand-in, if you use a computer to try to randomize things, is in some way absolutely and completely predetermined in the past. And you just have to go back further and further into the past to find exactly where these things are fixed and determined, to the point where it's somehow ultimately fixed from the initial conditions of the universe. It's baked into what the universe is, that everything that seems to be random or free that will happen is baked into the initial conditions of the universe. It's enough to, in a certain sense, so this quandary of diving into these depths, these details of quantum mechanics, things do get weird and messy. There is this seeming spooky action at a distance, or this many worlds branching, and in a certain sense, it's it causes some to have a certain affinity to go back to just the simplicity of classical physics, which itself was a nice and clean deterministic way of seeing the world. Unfortunately, the problem of seeking something like determinism, even in classical physics, seems to have been mistaken. So one of those experimenters who worked on these very complicated quantum mechanical experiments based off of the work of John Bell, named Nicholas Jessen, has argued that there is actually a dichotomy between determinism and indeterminism, even in classical physics. That, well, on the surface of it, as anyone who's sort of taught or learns classical physics, you're taught that it's a deterministic system, that if you know the initial conditions, you apply the laws to those initial conditions, and you can predict exactly what's going to happen. Now, when you're learning this, you usually pick the easy problems, a block on a ramp, or a simple pendulum, or the orbits of the planets. In practice, we know that most real dynamical systems, the flapping of a flag in the wind, the weather, even if we think of those as classical systems, we realize they are so complicated that we would never be able to conceive of all of those initial conditions. But the presumption is those initial conditions are there somewhere, and they must be exact. And so if they were exact in the classical picture, then physics would just work forward exactly. Now, there's a now, in one sense, though, the only limitation in the exactness of classical physics is thought by most people to be a practical one of calculation. How much can we figure out? But actually, but let's pause to think for a minute what that actually would mean. So, the idea is that every piece of data you might think about as an initial condition, the position or velocity of some particle or some aspect of reality, you apply a number to it. And you want to, if you need a really detailed number, you use a real number. So, a number with lots of digits after the decimal place. Now, if we think about real numbers, right, some of them carry a finite amount of information. So 1 is a finite amount of information. 3/5, that's a finite amount of information. 2.4573, that's a finite amount of information. Even pi is a finite amount of information. There's an infinite number of digits in there, but I can write a simple finite computer program to calculate pi. So if we think about the number of real numbers that have a finite amount of information in them, we get roughly 0% of the real numbers. The vast majority of the real numbers, by an absurd measure, actually have an infinite amount of digits in them. If you tried to write them to distinguish one number from another, it would take an absurd, it would take a nearly infinite number of digits after them. And so if we're going to actually have complete accuracy, the accuracy we would need to describe such chaotic and crazy systems as the weather or the wind flapping, we would need that nearly, if not actually infinite amount of information for each and every piece of data we start with. But on the flip side of this, there is very strong physical evidence that information, as even that quantitative idea of information, is strongly linked to entropy. And there are limits to how much entropy can be fit into a finite space. This is an important aspect in our understanding of black holes and the decay of black holes, and I don't want to go into the details there. But there is strong theorems and strong evidence that there is a physical limit to how much information can fit into a finite space. So the argument that Jessen is making is that it is impossible to have actually real numbers, actually infinitely amount of information, infinite number of digit real numbers in any finite system. That there must be some built-in cutoff, even in the classical world. That while we might have hoped for a perfectly deterministic physical world, that was we might have thought that we could translate this perfect infinite information we think about in mathematics, that there was no way to actually ever make that real in the physical world. That we never actually should have expected classical physics itself to be deterministic. That there's a way in which physics approaches determinism, and it's easiest and cleanest and most beautiful sometimes when it does. But our hope that physics would give us an absolutely deterministic picture of the world was a false hope from the beginning. So I'm going to come back to that link between math and physics a little bit later, but I want to shift into what I'm less comfortable about, which is the conversation about neuroscience. So, in 1965, a pair of German neuroscientists, Kornhuber and Dieck, and I apologize for my bad German pronunciations here, but discovered what they called the readiness potential. Well, they have a much longer German noun for it. I'm not going to try to pronounce. But the readiness potential was a characteristic electrical signal in the brain that showed up on EEGs, electrical tests that could be, or sort of these rigs that could be attached to someone's skull to test the electrical signals, which reliably preceded self-initiated movement. So they asked people to tap their finger, and they measured when the finger moved and when the signals came, and the signal preceded the motion of the finger by roughly 500 milliseconds, about half a second. In the 70s and 80s, Benjamin Libet at the University of California, San Francisco added a twist to this by asking participants to note exactly when they felt the urge to move. So there's three different times we're talking about. There's the time the finger actually moves, and the time the signal is recognized in the brain. So that was known to be separated by 500 milliseconds, but he added a third. When does the person in the experiment recognize the desire to move, the urge to move? And what he found was that the conscious awareness of the desire to move only preceded the movement of the finger, the desire to move also preceded, the desire to move the finger preceded the movement of the finger by only 150 milliseconds. Roughly 350 milliseconds after the brain had already started working, after there was some sort of electrical signal. From this, Libet was much more careful, but many people have read his experiment and say, this proves it. The brain moves, then I realize I want to do something, then I do something. Therefore, I'm not actually deciding anything. My brain is the first mover, and I am just a puppet of my brain. Even my desires are just a puppet of the electrical signals firing in my brain. Now, this is a caricature, but that sort of caricature is not uncommon in certain popular presentations of this experiment. Now, unfortunately, fortunately, science is rarely as neat and tidy as what you remember from your most recent popular science video. From the beginning, there were debates about this experiment, its methodology, its presuppositions, its results, and has spurred a very fascinating and amazing subdiscipline of neuroscience, specifically trying to hone in on this question of free will and free action and whether it exists. And perhaps not surprisingly, you find strong opinions on both sides from researchers in the field and from philosophers who study their work. Now, I'm no expert in neuroscience, but I want to present a few things that come from the good research that has come out of or good arguments that have come, research that has come from some from the neuroscientific side and some from the philosophical side. If you're interested in this, there's a good sort of summary of the history of this in Albert Mele, M-E-L-E, in his book Free. I'm not going to go into all those details. What I want to point out is one fairly recent contribution to this discussion that argues from within neuroscience itself that the Libet experiment may not be as significant as it was once thought. This is the work of Aaron Schroeder of the National Institute of Health in Paris. So he and his colleagues took a step back and tried to figure out, well, what exactly is this readiness potential, this signal in the brain that had become so familiar? He had already been studying various spontaneous background fluctuations of brain activity, various just activity in the brain when nothing significant is going on. And when you look at these over a long period, they look something like maybe a stock ticker, kind of fluctuating up and down, generally going up and down with spikes and troughs, and general trends upwards and downwards as time goes along. What he realized is that the readiness potential looked a lot like a zoomed-in picture of the edges of that background fluctuation, particularly when you look at the high points, that these highest peaks of this sort of stock ticker background motion looked a lot when you zoomed in on them, kind of like the readiness potential that had been the tool for the Libet experiments. So his group did a lot of testing and study and data analysis on brain activity of people at rest, not doing anything, people doing Libet-style experiments where they're like preparing to move their finger and noticing when they're moving their finger, and applied all sorts of data analysis to this. And his work, the results of his work are that from this active, the results of his conclusions from this work are that the brain activity corresponding to no motion, just the background, you're just sitting there, tended to diverge, so it separates from the brain activity of the Libet-style sort of finger motion activity, not at that sort of 500 millisecond moment that was pointed out in the original readiness potential experiments, but right at about 150 milliseconds, roughly when people were saying they had the urge to move. So that before there was the conscious idea of trying to move, that the readiness potential and this random background motion were fairly similar. And it was a sort of accidental feature of the way they did the data analysis originally that picked out 500 milliseconds, when in fact a careful analysis showed that the variation is actually closer to 150 milliseconds. Now, what exactly these background fluctuations that are the readiness potential are related to is, again, this a great series, a source for debate among neuroscientists. But one argument put forward by Sugar and others is that perhaps this is a sort of way to tip the scale in open situations. So, for those of you who have studied some more classical philosophy, this is, in a certain sense, this is a built-in tool to solve the question of Buridan's ass. So you have a donkey sitting here, and you have a great field of hay on the right, and an equally appealing field of hay on the left. He's equidistant from the two of them, and he can't decide which one he's going to eat, so he starves. He sits there and doesn't move. Now that doesn't actually happen, and one argument is that there's a built-in feature in nature that when there are very similar things, it sort of tips us in one direction or another. Now, again, this is a much debated point, but I find it interesting, the link to older medieval problems. Now, I want to say a few more things, though, because even supposing that the Libet experiment really is doing what it claims to do, or what some people claim that it does, showing a causal activity in the brain that precedes conscious awareness of the desire to move. There is a big step from that to an argument that we don't have free will. Free will is a complicated and convoluted topic among philosophers, and there's varying emphases and definitions, and I don't want to spend too much time trying to parse out all of those things. In one sense, it's just remarkable that anyone was able to sort of try and figure out a way to come close, to figure out a way to isolate something like free will in an experiment. It's something very creative and amazing what Libet was able to come together. But we have to be careful to see, okay, what was he actually measuring? And does it actually look like what we would want to call free will? In many ways, Libet apparently tried to be as non-committal from a philosophical perspective, as general as possible in designing his experiment. And so the instructions he gave to his subjects tried not to suppose too much. Unfortunately, what we're left with is a very vague, or a very odd situation. So let me describe. So there's, before I get into that, so there's a ton of literature in the neuroscience itself about what exactly is free will, what exactly are the implications of free will for neuroscience. And in a myriad of ways, what I'm getting into here draws on the work of Dr. Daniel Dehaene of Blackfriars in Oxford, who himself is trained in a broadly Thomistic tradition, but has actually spent several years embedded in a neuroscience lab at Cambridge as a philosopher, but working with neuroscientists and understanding their work and asking them questions. And so he has a very interesting perspective, and I found his reflections on this quite helpful. And he points out that the view of free will that is operationalized, that is turned into the thing we're going to test in our experiment, draws on what is commonly called the causal theory of action. So there are a number of presuppositions that come with this view of action. It broadly incorporates a human understanding of causation, that causes temporally precede their effects, but have no other real logical connection with them. In this case, the difference between a voluntary action and mere bodily movements is that the voluntary action had to have some sort of preceding mental cause. The mind, the soul, whatever, something did something, and then this bodily action happened. That's why it's voluntary. Whereas a spontaneous reaction or a tic is not voluntary. Some go so far as to say that this preceding mental cause must be recognized as such to be truly free and volitional. that we have to have a preceding mental cause, something going on in the brain. We have to realize that something's going on in the brain, and we have to choose to agree with and choose that activity in the brain, or at least go along with it before this bodily movement happens. And that is what's real free action. But this leads to some important questions. First, is there really no difference between voluntary actions and mere bodily movements, except some preceding mental activity? And in the midst of the action, are they really that indistinguishable? Is it only what happened before that tells us whether something is free or not? Or is there something about the activity itself that is different if it's free versus just a reaction? Second, do I have to be consciously aware of that preceding mental activity for it to be volition, to be willed? And third, is the only real access that we can have to whether an activity is willed, is a willed action, is if I or the person who's doing it is conscious of their intention prior to that event and willing to share it with us. So if I'm looking at you, I don't actually know if you're acting freely until I ask you the question, are you acting freely? And you tell me you actually had this mental activity and you're willing to share it with me. Up until then, I don't know. Is that really how we should think and understand about free will? So again, there are lots of there are lots of alternative conceptions of free will that don't fall into that sort of category of this causal theory of action. And the one that I, perhaps not surprisingly, find particularly compelling is the view of free will coming out of the Thomist tradition. Now, this view presents a much broader understanding of causality in general that is not primarily about prior events. Yes, at times, causality is about this happens first, and then something else happens, but that's not the only aspect of what causality is. That there is causality that is there's a broader and deeper understanding of the notion of what a cause is and the ways in which causes act. A broader understanding of what volition is, that we are sometimes aware of and sometimes less immediately so. That volition is not primarily about my recognition of what's going on in my brain, but about something deeper in human activity. So I don't have time to sort of explicate a full Thomistic understanding of free will, but I want to focus on a few particular aspects that I think help clarify why the lived experiment probably isn't the best tool for trying to measure a healthy conception of what free will is. Because a Thomist understanding of human activity allows for the possibility of free inactivity. I can freely choose to not do something, in which we choose to simply endure something patiently. So there is freedom even when there is no obvious bodily movement that follows afterwards. I can just sit still and not change anything, and yet that is there's a free choice involved in my willingness to endure something, whether painful or pleasurable. As well as the possibility of non-deliberative free action. Free actions that don't require preceding conscious thought and choice and deliberation in some complicated series of syllogisms and thoughts or arguments. Clearly, at times we do deliberate. At times we think deeply about what we are going to do. But some philosophers go so far as to say that the only time that we are actually exercising our freedom is when we are doing that conscious and worked out deliberation. That if we're not aware of that deliberation, then freedom isn't actually acting. But in that any sort of automatic activity we might have is not truly free, but is only free insofar perhaps as it inherits from some previously worked out and chosen free action. Aquinas has a much more expansive notion of what free human activity is that fills up the vast majority of human life. Not everything, but the vast majority of what we do. If you think about your morning routine of getting to work or getting to class, right? Much of it very well might be automatic. Myself, I'm imagining when I used to actually go to work before I was at Dominican, when I was in graduate school, I had to drive to the lab to do my work. And so I would get up, I'd leave the house, start the car, I'd turn left down Campus Drive. I would go through, there was a light and I had to wait for light. But I was not consciously deliberating every single time I drove to work, every single choice I had to make. There are times when experientially, I got in the car and I'm listening to some song or thinking about some problem I got to work out, and then I realized I've arrived at work. Now, I was aware of what I was doing in some extent. I was choosing to go to work. I chose to make all of the turns I needed to, but there wasn't deliberation about every single activity. And there is something of freedom from a Thomistic perspective, even in that, even if it is in a certain sense less conscious and aware. I think a good bit of the time, for instance, even today, right, I took a lot of time thinking through what I was going to say in this talk. Perhaps not enough, but in most conversations, we don't stop and run through the conversation in our mind and then play it out. There are times when that does happen, but someone asks us a question and we react. There is an immediacy in that reaction without some, at least definitely not, usually not, some conscious pre-deliberation and then activity, that we can be free even in seemingly immediate activities as well. Aquinas also has a robust understanding of non-voluntary action. Sometimes which he uses the phrase the acts of a human in contrast to voluntary human acts. Some of these are the automatic, shifting in our seats or scratching our nose when we really do them without willing or thinking. So there are certain things that can be non-voluntary, things that we do, but are just the products of our reactions. But so given that range of possibilities, I just want you to imagine for a minute the lived experiment and what the experience of being the lived experiment would be like. So imagine you're participating in this experiment. You are sitting in a room with a large contraption attached to your skull and a sort of clock or timer in front of you. You are told to wait for the clock to make a full rotation, and then at any time, whenever you feel like, flick your finger or your wrist. Just move your hand, whatever way you want. And you are explicitly told to let the urge to act appear on its own at any time without any pre-planning or concentrating on when to act. Be spontaneous. So the participants were told to not plan, okay, I'm going to wait 10 seconds, and then I'm going to go. It's just sit there, and whenever you get the slightest urge, just move your finger. Also, as a participant in the experiment, that there are experimenters watching every move you make while you're doing this. So if you sat and waited there for, 35 minutes before you moved your finger, you realize you're probably annoying some people. And so there are other aspects of this that are coming in as well. Now, I want to emphasize that because this is a strange and uncommon situation. It's very rare that we are consciously trying to not be conscious of things, that we are consciously trying to be spontaneous. To let an urge happen is not a normal sense in which we think about voluntary and free activity. It's interesting, but it is not the normal way in which most, or I think anyone, would really talk about free activity. Either deliberative or even a sort of automatic free activity, like I was describing in, going to work, following the path you've always taken. In many ways, from a Thomistic perspective, this seeming unconscious, spontaneous urge to move is actually a paradigmatic non-action, just a passive bodily reaction. It is the mind, doing something without our actual, without the mind moving us, the imagination or some physical reaction moving us without necessarily our being in control of it. If you allow me briefly to put on my priest hat for a moment, the closest, or a close analogy to this, I think, are the sorts of random urges and thoughts that come up unplanned when we try to quiet our minds. For instance, when people try to pray. If you ask anyone who has ever tried to develop a habit of mental prayer, quiet prayer, the mind can be our best friend and our worst enemy, as images and thoughts and urges pop up here and there. Sometimes there are things that we were thinking about just a moment ago. Sometimes there are things that we haven't thought about for years, and they just pop into the brain. unannounced. At times these can be helpful, but often they can be distracting or even harmful. These are not, from a Thomistic understanding, voluntary urges. When that image pops into the mind, we have not chosen it. We have not chosen for that image to pop into our mind. And there is no, and importantly from a pastoral perspective, there is no malice or goodness in the image that pops into the mind initially. At worst, these are temptations, if they're bad, pre-voluntary urges that we can choose to follow or not. And our freedom, and therefore the morality of them, is how we react to these urges and images that pop into the mind. In a certain sense, I think in the lived experiment, it seems that the subject is being told to prepare for a general sort of urge of some kind, and when it appears, to freely respond as quickly as possible. So the freedom is, in a certain sense, in the reaction to the mind, less than in the thing the urge that pops into the mind itself. Now, so this is an interesting and psychological and neurological phenomenon. Why is it that certain images or urges do pop into the mind? Why and how is it that we can react to them? But it's not a neat and clean case of free will, as is often presented in contemporary conversations. And arguably, from a Thomistic perspective, it's not a case of free will at all. That the urge itself is actually an act of a human, a non-voluntary thing, towards which we then choose to act or not. So, in this last portion of the talk, I want to so having set up this idea that from this perspective of physics, there seem to be strong arguments that, or at least an inclination among a lot of physicists and philosophers to presume that physics either is deterministic or really should be deterministic, and that if it's not deterministic, we need to figure out how to make it deterministic again. But that ultimately that inclination towards determinism is actually a flawed understanding of what physics can and should be doing. And from the side of neuroscience, that these measurements and experiments about free will that some people claim are measuring when free will happens, it's not so clear that what they're measuring actually is what we want to call free will. But in this last question, I want to shift and change the question in a slightly different way and ask, what does it mean to do science itself? What does it mean to do any of these experiments, whether it's deliberate experiments or these complicated experiments involving electrons and photons? I mean, everyone broadly agrees that science works, but what aspects of, or what is it that makes science work in the way that it does? For the sake of time and brevity, I'm not going to try to give a long defense of what the scientific method is, but in short, it involves formulating questions, proposing ideas, and testing them experimentally, predicting them, making a prediction that's some logical consequence of some hypothesis, and testing it by experimentation, followed by various analyses. Did the hypothesis work or not? Now, while that would work in your maybe middle school or high school, your secondary school science class, you turn that in, this is the scientific method. In actual practice, science as done by contemporary scientists also involves, can I replicate that experiment? Can I do it again? Can someone else do it? Can I survive external review where somebody comes and criticizes my experiment, whether it works or not? Can I, the whole processes of data comparing and sharing, and this whole social interactive network of people in the process of doing science. So already, if you just think through what we've described, a huge amount of rational interaction and choice seems to be implicit at every stage of this. If you think about the lived experiment, right, there is a certain amount of creativity and ingenuity required to simply find and measure the readiness potential. How did you find that electrical signal initially with equipment from the 1960s? And then the decision to isolate the awareness of the person being tested by living with this particular clock. There's something creative and interesting about that. The process of arguing over and defending that experiment has produced all sorts of interaction and social consequences, all sorts of arguments back and forth, all sorts of attempts to redo the experiment with better methodologies or different methodologies. It's been, and then the same thing could be said of those experiments testing Bell's inequality, or any experiment we would think about. The amount of precise control over very minute details is fundamental to everything that we do in contemporary science. If we don't have something along the lines of what, again, this Dr. Daniel DeHaan, I'm sort of poaching this phrase from him, if we don't have some sort of embodied rational control as human persons, the very possibility of doing science falls apart. If there's not some independent reasoning process by which we're able to look at what we have studied, think about what we don't understand, and decide and decide how to arrange things in order to test things that we haven't understood yet. We don't have some ability to have control over first our own bodies and then the bodies around us, the various EEG machines, the various experimental devices and techniques that you would use. I'm sorry, this is the theoretical physicist in me. I didn't actually do a lot of experiments, so I'm forgetting the description of that. No, but how do we have so how exactly is it that so we have to have this rationality, we have to have a certain amount of control over ourselves and over other bodies, and an ability then to communicate that to others in some collective social project. If there is no such thing, if there were no such thing as free will, if we didn't have that freedom, if we weren't actually in control, how is it that we are different from the dials and knobs and devices that we're turning? If we aren't actually free, how are we not just very complicated additional pieces of experimental equipment? How is it that we can have confidence that the thoughts that we have, about the experiment, the arguments we make about the experiment in defending them against other scientists, how can we claim to have, how can we have confidence that these thoughts and the results that we claim to be able to measure and come to from these experiments actually correspond to something in reality, and are not just some useful circuit in some larger experimental device that we happen to be part of and not be aware of? Who is running that experiment if we aren't? How do we know it is a well-designed experiment? How do we know that it's actually designed to come to the truth if we're not the ones who have some sort of ability to judge and determine if it's a good experiment or bad experiment? How do we know if it's even aimed at achieving the truth, if not aimed at something else? Why should we trust the scientific results at all if we don't have some independent control, this embodied rational control in the activity of doing scientific experiments, including those experiments that have convinced people that we don't have free will? So there's, what I want to conclude with is a question of why is it that we have this tendency, at least in some circles, among scientists and philosophers, particularly I would say those of a more mathematical or theoretical bent, to find something like these arguments against free will so compelling. I mean, there is a constant temptation towards imagining that we are not embodied rational creatures, but somehow some sort of independent minds. That we're not actually stuck in these cages of flesh, but that we're somehow Platonic minds outside of that, maybe a Cartesian mind that has some weird control over the body. And I think, again, this is particularly true among more sort of theoretical disciplines, mathematics, theoretical physics, and philosophy sometimes. In one sense, again, but there's a huge danger in treating the physical world like a math problem or a logic game, which dates back to the scientific revolution itself. So Descartes, right? So Descartes was a brilliant mathematician who had solved math problems no one in the history of the world had solved before. And he was convinced that if the world were really just a complicated geometry problem, we could solve it, get an answer. He went about doing just that, imagining a physical world that's simply to be the equivalent to sort of three-dimensional space divided up into tiny bits. And he sort of tried to solve this problem, and he came up with his vortex theory of the planets, which is amazing and beautiful and creative and wrong. It's just not true. He convinced an entire generation of investigators that a good explanation had to be a complete explanation, kind of analogous in some ways to those perfect deterministic real number solutions, where you had to explain something down to the smallest and tiniest pieces and how the smallest and tiniest pieces push on one another. In reaction to this, Newton proposed a different way of thinking about the physical world. He was convinced as well of the power of mathematics, but he recognized that math is a tool to describe reality and not the reality itself. Further, he insisted that he could recognize, model, and mathematically explain various phenomena like gravity without actually knowing exactly how every single detail of causes and effects were working down to the minutest detail. It's a famous quote from his general schooling at the end of his Principia Mathematica. I have not as yet been able to discover the reason for these properties of gravity from phenomenon, the topic of this great work, and I do not feign hypotheses. For whatever is not deduced from the physical phenomenon must be called a hypothesis. And hypotheses, whether metaphysical or physical, based on occult qualities or mechanical, have no place in experimental philosophy. In this philosophy, particular propositions are inferred from the phenomenon, and afterward rendered general by induction. Newton is saying that we can have confidence, we can provide very good mathematical descriptions of reality without there needing to be absolute and complete descriptions of reality, without having the mathematics needing to mirror the physical reality in every minute detail. And Newton won the day, practically speaking, in the history of physics. But ever since, I think physicists in particular have had to be particularly careful about letting their mathematical ideas run too far ahead of their experiments. You can see this in theories of imponderable fluids or the luminiferous ether of the 19th century, where the math seemed to work so well and seemed to imply certain physical realities, and the presumption that, well, it just has to be there. The math works so well, it's got to be this way. And I would argue that even today's theoretical physicists can fall into the same temptation, taking the beauty and order of their theories as more important than our own experience of the world. In a sense, quantum mechanics has made this even worse to a certain way. It has confirmed for us that the real world is even stranger than we thought. There really is things like this spooky action at distance going on, this unpredictability. So there's some things that are very counterintuitive about reality, unimaginable in fact. So there is even a certain pride among some physicists that physics contradicts common sense. It's seen as a feature, not a problem. And so when they find a physical theory that they love the mathematics of it, and they say, well, yes, but this implies something really weird about experience. It implies that the universe branches into millions of parts, that we don't have free will. That it's like, well, that's actually kind of cool. I kind of like that. There's a way in which physicists kind of get pulled into that sort of direction. It's striking to me that a particularly what I found helpful expression of this problem was made by the same Professor Giesen I mentioned before, who was doing those very complicated experiments about quantum mechanics. He mentions arguing with a famous theoretical physicist about the many-worlds interpretation of quantum mechanics that I mentioned at the beginning. And he says that the many-worlds interpretation of quantum mechanics fails the test of Occam's razor. You are positing way more aspects of reality than are needed to explain the situation. And so he says that just this very idea is contrary to this classic standard idea of Occam's razor of not positing more things than you need. And he quotes this theoretical physicist's response as, Occam's razor should not be applied to the physical world, but it should be applied to the Schrodinger's equation, the best equation we have in the mathematics of quantum mechanics. Don't add any terms to this utterly beautiful equation. Now, there seems to be perhaps something a little tongue-in-cheek in that response, but there's a way in which it's symptomatic of a lot of physicists, and this is what I'm most familiar with. And I think there are pieces of that show up in other disciplines of the sciences as well. Taking the sort of beauty and order of a physical theory as more important than our own experience of the world, forgetting that it is through our very experience that we have come to develop these theories that we find. This brings me back around then to my initial fear. My fear about trying to answer the physics of free will question. So perhaps I've done enough to argue that free will is real. That our very experience of reality, and in fact the very fact that we are able to do science and to produce reasonable results about scientific theories about the world, is actually a sign that free will is present and necessary in human life, and a confirmation of our experience of free will on a more common level. Perhaps you're still doubting. Perhaps you're withholding judgment until someone gives you that convincing argument for exactly how the mind pushes around electrons. For now, I'm going to simply just steal unabashedly from Newton. Hypothesis non fingo. I feign no hypothesis. I do have some random conjectures about how that might work. What weird little way in which you might tweak quantum field theory or something like that. But for now, I wonder if, but I often waver between thinking that I can see a reasonable picture for thinking that it's working, or whether it's something that we would never, in principle, actually be able to observe. For now, what I am convinced about is that science does leave room for free will. But even more than that, I am convinced, and I think that there is a lot of weight behind the idea that science needs free will. The very possibility of doing science requires this embodied rational control, one aspect of which is our free activity. I am further convinced that if we are ever able going to discover some sort of mechanism, some sort of description of how our immaterial will might be able to act with physical or interact with physical things, it's going to have to start from the top down, not from the bottom up. Jumping straight to quantum mechanics and particle physics is probably not the right place to start. There's going to need to be much more careful reflection on what exactly free will is and how it shows up in human activity. How can we recognize it in human activity, and how can we even begin to do biological and neuroscientific experiments on free will well? So we have to start with good neuroscience about what truly is free will, and not just things that kind of look like free will but really aren't. And then it would have to go down through molecular biology about what is the complicated molecular and chemical processes going on in all of those neurons in the brain, and then through chemistry, and then maybe then you might get to some grist for the mill for a particle physics type of answer about what exactly is going on between the immaterial soul and the physical world. I think trying to propose something at this point is really just premature guessing and speculation. So again, I'll conclude with that idea that I feel very, very strongly that not only does science leave room for free will, but science needs free will. And while we may not have a complete explanation for exactly how free will works in a technical and mechanical mode, we have very strong evidence that free will does work, and very little evidence, and very little reason to presume that it's not there. And that there is something reasonable about Newton's instinct that we shouldn't jump so far ahead of our experience. There's something reasonable about that idea to not feign hypotheses about exactly how the nitty-gritty details of free will works. So thank you very much.